Thank you. Thank you for coming and thank you for inviting me to speak on this wonderful meeting. I'm very happy to present the results from my postdoctoral stay at the Niels Bohr Institute, and I will try to also put them in a broader context of optomechanics and measurements and several other directions. So now I'm also working in the Center for Quantum Optical Technologies at the University of Warsaw. But as we continue collaboration with NBI, we also are looking at new ways on how to improve our measurements of those very interesting systems that I will be presenting. So we'll start maybe unusually because I will consider a rather fundamental question of how do we measure position of a mirror with light and where do the limitations arise. This will lead us to the more novel field, which is cavity quantum optomechanics, where those effects become unusually pronounced. And then, as we discover the limitations, we'll just consider how to beat them, which has been termed a method of canceling back action. We'll consider several, and our method is called the negative mass reference frame, but I hope to convey that it is nothing too unusual, rather just fancy engineering of susceptibilities. And finally, we'll use that to create a rather odd entangled pair. So first, consider a mirror of which we will reflect light, which is described by the quadratures here. And then we will also describe the mirror itself quantum mechanically. So we'll associate position momentum operators. So now, since the mirror will first consider to be a free mass, we can write those very simple equations of motion for the mirror, and we'll say that the mirror is acted upon by a force. The force will be consisting of a radiation pressure force that we'll write in just a moment, and a certain stochastic thermal force, which in principle can also represent, has a part that represents the ground state motion. That would be more simple if that was a harmonic oscillator, then it would have to have some ground state fluctuations. For simplicity, we consider the free mass, but it doesn't matter so much because those equations allow us to allow themselves to be solved in a Fourier domain, and we see that in general we just get that the position is the force is transduced to position by some susceptibility chi of omega. So once we have the motion, we need to consider what happens to the light. And here we already see that light acts upon motion. But in the light case, we will really be considering those quadratures. And the quadratures are consisting of the one that we will call amplitude and phase. So we'll just fix ourselves in this displaced frame of reference in the phase space. And we'll say that the y quadrature represents the phase, while the x quadrature represents amplitude fluctuations. So we can obviously see that if we just rewrite x plus iy as a scaled phasor, and then we just ask a simple question: what happens to the light once it bounces back off the mirror? And the primary effect is the phase change proportional to the position of the mirror. So now, to link the two pictures, we need to remember what is the radiation pressure force, and for that we focus our attention on this displaced effect. So we get alpha, a big coherent state, plus some fluctuations around it, and we see that the radiation pressure source is a very big scalar term that will just push the mirror, plus some tiny fluctuations. And of course, we will be interested in just the tiny fluctuations because the first term is I would say, classical. So now, on the other hand, we can rewrite the fully how will the light quadrature, in particular the phase quadrature, behave upon such interaction. And we see that it will, due to the phase term, it will pick up the motion of the mirror in two terms, one of which is proportional to the amplitude, while the other one is proportional to the intensity, because the motion itself was created from light. So now if we write a naive estimator of what we would say from the measurement here is the position of the mirror, we see a trade-off or a scaling here. So we have the noise, the initial noise. This is shot noise. Then we have the motion, the two terms associated with the motion. But the first motion, the first term is really just the thermal or maybe the force that we do want to measure, while the other one is the one that we are creating with the measurement. Since the first term decays with alpha, while the last term grows with alpha, that suggests that there is a trade-off. And this trade-off is happens at a particular probe strength and is in this domain often called the standard quantum limit. It's perhaps a slightly overused name because different things are called standard quantum limits, but a good trade-off between shot noise and radiation pressure noise is where we want to measure. Interestingly, since we see that while the shot noise does not depend on the frequency of interest, while the radiation pressure noise is transduced via the susceptibility, then the point at which the standard quantum limit sits in this respect also depends on the frequency. So in general, even for a fixed probe strength, we'll get a curve in the frequency if we consider the sensitivity or the noise spectral density that limits this sensitivity. We see this curve that will just slide along the line called the standard quantum limit with changing probe strength. And in our system, so that was work from my colleagues, but they've been able to really change the probe strength and actually slide this curve very nicely. Now, to beat this sensitivity limits, it has already been long ago proposed that squeezed light may be used. So if we just squeeze the light in the phase quadrature, then we may gain sensitivity in the places where we are limited by the shot noise, while we will unfortunately also see the effect of anti-squeezing on the amplitude quadrature, which will increase the radiation pressure noise. And interestingly, this is what people already see in the gravitational wave detectors. So not even the systems that were supposed to be quantum like ours that I will show in a moment, but in those systems where you just really want to measure something very precisely. So people at LIGO have injected squeezed vacuum, and they see that while they gain sensitivity in this region, then for very low frequencies, the noise actually grows, and I think that's actually way better visible in the plot from the European detector, especially in the red curve. And that calls for some kind of solution that would allow us to shape the squeezing such that we can improve the sensitivity at all frequencies. Since the frequency is just the susceptibility of the free mass, which the mirrors are here almost free mass in this respect. So now we will say that, okay, so we want to use some kind of squeeze light, and we want to evade this back action of the radiation pressure noise on the mirror. And there have been several proposals, and this negative mass proposal is really just the following. We consider that we will bounce off this light from two mirrors. And as such, we will get not 2, but 4 terms that we read out. And the thermal or ground state noise of the second mirror will obviously be completely different. However, the backaction noises of the two mirrors will be driven by the same amplitude quadrature of quantum light x in. So suffice it to say, you just need to cancel those out, and you cancel the radiation pressure induced noise. And the condition for that is to just get the susceptibilities being opposite of each other. So it turns out that such susceptibility, while quite fixed for a mechanical system, can be tuned just like that for atomic systems, which has been realized in the group, even for example, 2 different atomic systems. So just by so this will be the essence. I just want to mention some other combinations. For example, you can utilize the fact that you don't have to measure the Y quadrature, but you can measure some rotated quadrature, and this may lead to interference between the a bit of X that you actually measure and the X that is in the phase quadrature. So that will allow improving the sensitivity on some frequencies where this interference is destructive only. And then there are some non-steady state methods, like for example stroboscopic measurements that work for an oscillator, but here we will try to focus on those steady state methods. So a good intuition to think about this negative mass is that if we get those two mirrors, one of which will, as it will turn out, is actually an atomic system, then if they can really feel the fluctuations of the photon number in the light field in an opposite way, then the distance between the two will actually change. Therefore, if we measure the position of one mirror in the reference frame of the other mirror, then this measurement will be unaffected by the radiation pressure. And really the susceptibility is the essence here. So if somebody wants to ask whether we have achieved a negative mass, then I always say no, it's just a susceptibility engineering. In any case, to observe those effects, we don't have a gravitational wave detector. We go to the nanoscale, and the oscillator that we work with has been developed mostly by Yagishet Saturian and Albert Schlisser. And those oscillators use several tricks to achieve excellent coherent properties. So first and foremost, they are very thin silicon nitride membranes that are very much tension, such that they, even if they were just a nice square, they would already have a quality factor on the order of millions. So they can do a million oscillations within the coherence time. However, what has been achieved here is adding to the system a phononic crystal structure. So a phononic crystal structure, you can imagine, is quite similar to the photonic crystals, but designed to reflect phonons back into the oscillator. So actually the oscillator is only the defect that is in the top left corner is seen as the blue, as the yellow dot. So this defect is the oscillator itself, while the structure around it is periodic, such that the frequency of the oscillations of the defect itself will be reflected as in a Bragg mirror back to the center of the entire structure. And this oscillation is, this effect is actually achieved by having a specific tension in this entire structure, such that such that the speed of sound is modulated periodically. And those oscillators can achieve cryogenic quality factors even up to 1 billion. Now we place, to achieve strong interaction with light, we place those oscillators in between two mirrors. So often it is considered that the so-called canonical optomechanical system is a mirror on a spring. Here we have two stationary mirrors and a membrane inside, but the membrane is reflective. Therefore it forms two subcavities, and those two subcavities allow efficient interaction without having to have this membrane highly reflective. So the cavity can be high finesse, but the membrane doesn't have to be very reflective. It can only reflect a few % of light, in fact. So not going much into details, the Hamiltonian of interaction will couple the position of the membrane and the phase of light that goes out of the cavity. And this is an example of our cavity. So the membrane is a chip like that. A few hundred microns in size is the silicon nitride resonator itself, and it is placed in a copper structure with the two mirrors and then put in a cryostat because we want to start already with a reasonable phonon occupation of the oscillator, but also because the material properties improve them in the cryogenic environment by itself. So nice effects that we can achieve, for example, are related to this interference effect, so that if we if we measure a quadrature that is rotated with respect to phase or amplitude, then we can interfere the different quantum fluctuations and see strong squeezing outside of the cavity that can even be a few decibel easily, and it's actually not limited by the coherence of the oscillator itself, but the losses of the cavity. And furthermore, with Ivan, who is together with us on this conference, we have also worked on cooling this oscillator as much as we can to close to the ground state, and characterizing it with a set of very long cavities, because we need to filter out Stokes and anti-Stokes photons scattered by this oscillator, which are only a few megahertz away from the very strong laser field. So we have already achieved around 0.2 phonon occupation, so that is quite close to the ground state, and it's an example that's one of those long filtering cavities. So here the cavities for filtering are even more complex than the mechanical cavity itself. The other system are the spins. So the spins are cesium atoms. It's a collective excitations inside an atomic ensemble that sit in a microchannel. This microchannel is coated with alkene coating that allow the spins to bounce back and forth and not lose the spin coherence, or at least lose only a little bit of it. And we pump those spins into a maximal MF state in one of the ground state manifolds of cesium, or the minimal one, really. So, regarding whether this spin orientation will be parallel or anti-parallel with the magnetic field, then the susceptibility of such spins to the light field, which interacts with the spins via Faraday rotation, will be either negative or positive as compared with the mechanical system. So now we link the two setups. So as I told you, the spins interact via Faraday rotation, therefore they are coupled to polarization quadratures rather than just the phase space quadratures. So we need an interferometer between atoms in the bottom left and the membrane in the top right that will map via a set of PBSs and wave plates the polarization quadratures, really the quantum fluctuations of polarization into the phase space. So the two systems have this free space light link, and then if we detect the light that passes through both systems, then we see the spin noise and the mechanical noise that comes from two different systems. So the blue is mechanics, it's not tunable, and the spins are actually tunable because it suffices to change the magnetic field. So now if we just change the magnetic field and we bring over the spins to the mechanics in terms of the frequency, then we indeed see that the overall noise is actually reduced. And we can quantify those noise contributions, and we see the ground state or thermal motions of both systems. And furthermore, we see that there is some back action, and this back action cannot be really said whether it's from this or the other system because they are working together now. So if we now consider what are we measuring with this detector, and if we go to the rotating reference frame, then we will find out that we are actually measuring EPR quadratures, so like x plus x and p minus p of the combinations of the two systems. Therefore, we can measure those EPR quadratures with very much reduced noise. And the noise contributions really are described in our paper and are quite more involved that I'm just showing, but this is because many more quadrature rotations that have to be taken into account in the theory. In essence, now if we can measure the two quadratures, then we can consider them. Then we can consider this measurement as a filtering task. So we want to filter the signal from the noise, and we want to estimate where our system sits in terms of those sum and difference quadratures. And the method for this is the so-called Wiener filter, which allows us to create an optimal estimator and together and allows us also to infer the conditional variance of this estimation, given that we know the steady state noises of the two systems. And since we are not doing any feedback or feed forward here, then the system is really steady state. We can say that we are starting measuring now, but that doesn't really affect the system itself. So we do not need to use the Kalman filter, which is a popular topic now, but the Wiener filter is actually just a simpler, more steady state version of the Kalman filter, and we just solve it. We solve those equations for the optimal filtering in the discrete case, which is a very well-known engineering task, just applied to quantum problem here, and we get the blue curve K, which is the Wiener filter, and we can see that it really can digitally filter optimally the signal here for the two systems, and then also reduces all the noise that is actually present in the system, but still takes it into account as a reduced conditional variance. And I want to mention that this Wiener filtering can be cast into the stochastic master equation formalism, which I think nicely allows us to say that at some time 0, we start measuring the system, and as we gather more and more information, then our conditional variance of our estimator reduces. And most importantly, it reduces to below the so-called ground state of the joint two systems, which simply means that those two systems are getting entangled by are getting conditionally entangled by our measurement, which is achieved thanks to cancellation of some of the noise due to quantum interference of noises. And we can get this entanglement for various sets of parameters, and we can get it to around 0.8, so 20% below the bound for the EPR type entanglement. So we have to fight all those various types of noises, and they are being fought both physically, so this is somewhat after already much work, and then digitally. But just to give you the idea of the experimental systems are not that pure. Now, I want to mention two applications. So one is how do we merge such system, which is the negative mass spin ensemble with the gravitational wave detectors. Main problem is that they don't cooperate at the same wavelength because the atoms require a very specific frequency to interact nicely. And it has been proposed that it would be nice to generate entangled light and send one of the beams resonant to atoms to the atoms, and then the other to the gravitational wave detector. And again, via measurement of both systems, actually this, we can say that this, we do not need to use the same beam because we can, in a way, swap the entanglement between the two systems, so light and then the physical systems. Finally, I want to mention the other thing we are working on now in Warsaw is that we considered first theoretically that we can have some two mechanical modes that are close by each other, and we are asking, okay, so how do we estimate the difference between the two modes if they are lying like 0.1 of the sigma close to each other? Then it's impossible to just do it with a spectroscopy that we do with our quantum memory. So we have created an interferometric setup that processes such light fields inside the quantum memory. And here I won't explain much more because we also have a poster of that. So I invite you also to talk with us or Mateusz Mazelanik, who worked on that. And we are now also working. We have pretty much last week created first Rydberg atoms, so we'll be moving towards some stronger interactions between those atoms. And I invite everybody to collaborate if you have nice ideas. So I would like to thank both the Copenhagen and the Warsaw collaborators, and thank you for your attention.
So thanks a lot. Perfect timing. So questions? Also,
I didn't.
I think yes.
Okay, so I didn't understand one thing. The mirrors, of course, interact with the environment, and they have their own dissipative or dephasing dynamics. You take into account in your equation the fluctuating force, which you call this thermal force, but I didn't see any damping coefficients, and fluctuation dissipation theorem, of course, requires.
Yes, I didn't put it there. The damping, so that was the first slide that was supposed to give the intuition of the measurement problem. The damping is very well included in this theory. So it is indeed true that the susceptibilities here, they need to be complex with the damping coefficients. And these damping coefficients are really strictly related to the so interestingly, for the spins, we have very little thermal noise, and this is well linked to damping, and the damping is mostly due to collisions of the atoms with the walls. Mechanics is completely crazy. It has a millihertz damping coefficient, and then it is so strongly interacting with light, then the damping is actually all due to the interaction with the light field. So the membrane mode is broadened from 1 millihertz to several kilohertz, like here, by interaction with light. So in a way, it's sideband cooling.
Okay. Any other questions? Maybe online. I don't know what to. Oh, you're taking. Okay, so thank you again.
Thanks.